Alright, so this video will be for the solutions for the paper 1A questions for E2 quantum physics. Our first question is a Compton scattering question. Okay, so we have photon of wavelength lambda scatters of an electron at rest. Scattered photon has wavelength lambda prime, which is going to be a longer wavelength because it's lower energy, because some of the energy went to the electron. So energy will be conserved in a collision, and so the original photon energy is transferred to the electron and then the photon energy after. And so we want to know how much energy goes to the electron. So we know that energy is hc over lambda. So we have hc over lambda before is the electron energy plus hc over lambda prime. And so the electron energy is 1 over hc over lambda minus hc over lambda prime, which is 1 over lambda minus 1 over lambda prime. Which is not an answer choice. But it says what is the fraction of the incident photon energy that gets transferred to the electron. So it's not actually asking about the energy that gets transferred to the electron, but what is the fraction of the original, which of course, I don't know why they're overcomplicating this, but let's break it down a little further. I also realized I eliminated the HC improperly. It's still there. So the fraction is going to be the electron energy divided by the original energy. And so the HC gets eliminated. And so we have 1 over lambda minus 1 over lambda prime all divided by lambda. Sorry, all divided by 1 over lambda. So if we just simplify the fractions, we eventually get, we multiply lambda times 1 over lambda minus 1 over lambda prime. We get lambda over lambda minus lambda over lambda prime, which is really 1 minus lambda over lambda prime. That really is the answer. They choose to rewrite it as D, and the way they're getting that, they're getting lambda prime minus lambda over lambda prime. I can show you where they arrive at that. If I rewrite 1 as lambda prime over lambda prime, which is legal, I get lambda prime over lambda prime minus lambda over lambda prime. If I combine the denominator, I get lambda prime minus lambda over lambda prime, which is, in fact, choice D. So in typical IB fashion, they start with a pretty basic principle and then start monkeying around the fractions and getting very annoying. That is the principle. And again, like, we kind of get lost in the weeds in terms of the fractions and whatnot, but it's just a question of conservation of energy, really. And just don't forget the formulas for energy based on frequency and wavelength. HF for frequency, HC over lambda for wavelength. Next question. We have monochromatic light. Frequency F1 is incidence on the surface of a metal. So this is going to be photoelectric effect. Stopping voltage is V1. When the frequency of the radiation is changed to F2, the stopping voltage is V2. What is the quantity V2 minus V1 over F2 minus F1 equal to? I also want to point out that the weird way the page is broke, it's either H over E, H over C, or up here, HC over E. And it tells us the answer is B, but let's get there. So let's first talk about stopping voltage and what that has to do, how that relates to the kinetic energy of the electrons, because the photoelectric effect equation, so the energy of the electrons that are coming off of the photosensitive surface is equal to h times the frequency of the photons hitting the surface minus this thing called the work function. And so basically, the frequency of the light has to be high enough so that HF is greater than or equal to the work function, so that you can actually have a kinetic energy. Because if the frequency is too low, then that loss of the work function, the electrons are simply not going to leave the photosensitive surface. You need a frequency that's high enough. But I say, well, like, where does voltage come in here? Like, I don't see voltage anywhere in this equation. And so the voltage actually has to do with the energy of the electrons. And so it's kind of like, how can you actually figure out from the photoelectric experiment, how could you figure out the energy of the electrons that are coming off of the photosensitive surface? So the setup for the photoelectric experiment is not just a photosensitive surface, but rather it's a set of parallel plates where there's a illuminated plate and there's a collector plate. But the thing is that the collector plate is actually negative. And you might be like, no, wait a minute. We're talking about electrons here that are being emitted from the photosensitive plate. Why would they be going over? Why would they be crossing the gap and going over to the negative collector plate? It's negative. Why isn't the negative plate repelling the electrons? It is, and that's the notion of the stopping voltage, and that's actually how we figure out the kinetic energy. So here's the deal. So the light photons, they give the electrons from the illuminated plate energy to cross the gap. That's like they're getting that kinetic energy of the electrons to cross against the electric field to the negative plate. But what if we varied the voltage? So vary the voltage coming from the variable power supply. Eventually, if you kick up the voltage, there'll be enough repelling field that the electrons don't have enough energy to cross the gap. So yeah, if you increase the voltage, it'll stop the electrons from crossing. Now, as you change the voltage, for a low voltage, the electrons can cross, but then if you dial the voltage up, eventually you stop the electrons from crossing. That is what stopping voltage is. So yeah, the stopping voltage is the voltage at which you stop right at the point when the electron flow stops, when that current goes to zero. So like for instance, if I were to put an ammeter into the circuit, like if I stuck an ammeter into that circuit, the ammeter is going to drop to zero as you change the voltage. Here, I wrote V. Let's actually draw that as a voltmeter. Ding. And so like as you change the voltage of that power supply, increase the voltage to the point that the current drops to zero. That voltage number is the stopping voltage, and that's what they are talking about. Now, what the heck does that have to do with the energy of the electrons? Well, let's recall that V equals W over Q. So W equals QV, and work is energy. So the energy, max kinetic energy of the electrons is QV. So, this is a long explanation, but in the end, Emax of the electrons equals HF minus the work function. Emax can also be represented as QV. Okay, so going back to the question, it says for one frequency has one stopping voltage, and another frequency has another stopping voltage, which makes sense because a higher frequency is going to be higher energy. So if it's a higher energy, it's going to be a higher stopping voltage to stop those electrons. Okay, well I just used up a lot of space, and now I need my space back. So yeah, we have QV equals HF minus the work function, but if we're going to talk about the stopping voltage, the voltage at which we stop the electrons from crossing the gap, the work function has already been achieved. We're already sending electrons across the gap, so then the frequency is high enough to overcome the work function. So the electrons are crossing the gap from one side to the other, and then you turn up the voltage to stop that current. So in other words, if we're talking about stopping voltage, QV is equal to HF. We no longer need to subtract out the work function because that work function energy has already been achieved. Now notice in the answer choices, they're using E for the electron instead of Q. And so based on the problems, we have two frequencies and two voltages. So we have EV1 equals HF1 and EV2 equals HF2. And it wants to know what's the difference in the stopping voltages, what's the ratio of the difference in the stopping voltages to the difference in the frequencies. And so when we throw it all together, we get the difference in the stopping voltages over the difference in the frequencies is HF2 over E minus HF1 over E. And we separate out the F2 minus F1, that's in the numerator and the denominator, so the frequencies cancel, and what I'm left with is Planck's constant divided by the charge. And so that is B, and which agrees with the mark scheme over here. Alrighty, number 3. Number 3, Compton scattering. And it says, which is true about Compton scattering? So Compton scattering, we have it is a light particle, a photon acting as a particle. Momentum, energy, and momentum are conserved in the collision, but some momentum and energy is transferred from the photon to the electron, and so there are changes as a result. So things that are true. So first of all, the energy of the photon does decrease because some of the energy goes from the photon to the electron. So that is true. B, the wavelength does not decrease, it increases, because E equals hc over lambda, so if the energy is going to decrease because it transfers some of its energy to the electron, then the wavelength is going to increase. So it's not B. Momentum of the photon is unchanged. No, because in the collision, some of the momentum is transferred to the electron, so not C. And then the combined momentum of the particles increases. No, because that would violate conservation of momentum if there's no outside forces, and there are no outside forces. And so A is the only thing that makes sense. Okay, moving on to number 4, where of course they broke the pages weirdly again. So let's see. Proton and alpha particle accelerated by the same electric potential difference. Kinetic energy of the proton is E. De Broglie wavelength is lambda. What's the kinetic energy and de Broglie wavelength of the alpha particle? Well, let's remember that an alpha particle is a helium nucleus with 2 protons and 2 neutrons. And the de Broglie wavelength is h over p, given by our data booklet, and p equals mv. So we're comparing kinetic energy and de Broglie wavelength of the alpha particle. They're accelerated by the same potential difference. So we know that energy is qv, which is 1/2 mv squared. It's not actually asking about the velocity, it's just asking about the energy. And so the alpha particle has, if energy is qv and they're accelerated by the same voltage, but the alpha particle has twice as much charge, it's going to wind up with twice as much kinetic energy. But as for the de Broglie wavelength, okay, so de Broglie wavelength is h over p, and p does equal mv, but I don't really know about the velocity, but I do know about the energy. I know that the alpha particle has twice as much energy as the proton. We already established that. So really right off the bat, the alpha is going to have more energy, so it's not choice A, and it's not choice B. But we do know from going all the way back to topic A that energy is momentum squared over 2 times the mass. So I can throw in, and if that's the case for energy, I can solve for momentum, and momentum is radical 2m times the energy. Proportionally speaking, I can get rid of the 2, right, because it's a constant. And I can get rid of the h, because it's also a constant. And so proportionally speaking, the wavelength is 1 over radical 4 times 2, because the alpha particle has 4 times the mass of a proton, because it's 2 protons and 2 neutrons, and twice the charge, because it's 2 protons, right? And so the wavelength is 1 over radical 8. Now, we don't have to really establish the 1 over radical 8. We just need to establish that the wavelength is either greater than or less than, and 1 over radical 8 is less than 1. So our alpha particle has a greater energy, but it has a smaller wavelength, has less than 1. It's a fraction of the wavelength of the, of the proton. But come to think of it, I just think I did a way more work than I needed to. Oh wait, no, we're talking about matter, not, and yeah, I can't use E equals hc over lambda because we're talking about a particle. We're not talking about a photon. Never mind. But anyway, yeah, so I did have to do all that. But it is C for that reason. Okay, next question, 5. Atom of hydrogen, atom of helium moving with the same kinetic energy. De Broglie wavelength of hydrogen is lambda h, and of the helium is lambda helium. What is the ratio? Man, they love those ratios. And actually, number 5 is very similar to number 4. C, number 4. And so we can establish that momentum, we already just established that, momentum is radical 2 times the mass times the energy. And it says that they have the same kinetic energy, but they're going to have different masses because they do have different numbers of nucleons. Hydrogen is just going to be m, and the helium is going to be 4m. So, yep, the hydrogen over the helium is h over radical 2m hydrogen times the kinetic energy divided by h over radical 2 mass of the helium times the kinetic energy. They have the same kinetic energy, the h cancels, So, and it's working at the compound fraction. Helium is 4 times the mass of the hydrogen, so we have rad 4 divided by rad 1, which winds up being 2. So the ratio of the hydrogen to the helium is 2, which is C. There you go. All right, number 6. How many total problems do I have here? I might have to split this video. Yeah, there are 26 problems, so I'm definitely going to have to split this video. All right, so maybe we'll do the first 13. Anyway, we're still on 6. Electron is accelerated from rest through 3.8 thousand volts, kilovolts. What is the de Broglie wavelength of the electron after its acceleration? And in millimeters, micrometers, nanometers, and picometers. Okay, so we have de Broglie wavelength is h over p. We know that kinetic energy is p squared over 2m. We also know that the energy, kinetic energy is of an electron accelerated through an electric field is qv. Seem to be gone out of focus, which is not good. Okay, we seem to be back in business. Okay, so we know that our charge is an electron and the voltage is 3.8 kilovolts.